Interactive theorem proving and other formal mathematics systems depend on underlying logics, and Naproche, like a few other systems, is working with first order logic. And I hope that we can still cover mathematics in first order logic. Therefore, the talk is called First Order Mathematics and Naproche. So let's be quick. First order logic, of course, you all know. Here is a snippet of something that undergraduates will see very early in their studies, and they will learn that you can that you can argue in first order logic using the usual things like cases, excluded middle, quantifier treatment, and so on. And then if you go further and introduce set theoretic axioms, then all of mathematics can be covered. Yeah, that's the standard view. This first order logic is also good in many other ways. Mainly I would say there is the Gödel completeness theorem, which equates formal reasoning in first order logic with truth under a standard truth definition. And it's also, I would say, a theoretical basis for formal mathematics, because when you have a proof, then you can find a proof, a formal proof, in the first order system. So I think this foundational theorem, I think, very much inspired formal mathematics from the beginning. First order logic has other theoretical properties. It's the strongest logic, modular equivalences and so, which satisfies the very good compactness theorem and also the Löwenheim-Skolem theorem. I don't want to go into details here. Another thing is Herbrand's theorem, which already leads in the direction of practical theorem proving. Okay, when you think of first order logic, and when you first come across it, you think that, okay, the objects are here on this screen, they move around. This is where the universal quantifier lives, so to speak. And then objects may be connected by some function symbol or function in an interpretation. So first thing is to equate the screen with the universe of first order logic, and then you might think, oh, this is rather weak because we are just talking, let's say, about a group here. But of course the thing gets much richer when you introduce strong axioms, and set theory is, of course, a first order logic system, or you can axiomatize set theory in first order, and then it gets rich because you can define interesting things like the class or the set of natural numbers. And really this can be taking place in a set theoretic universe where you have all sorts of other mathematical things available to you, like real numbers and functions and products and I don't know. So this is a standard view of the set theoretical foundations of mathematics, but many people are not quite satisfied with that because it sort of makes you think of 2 as being a set, whereas you rather would like to see it as a number. So it appears more natural to take this sort of apart and say, where the numbers, this is perhaps the natural numbers living within the real numbers, that is somehow outside sets. These are just objects, atoms, what you like. And then out of these things, these objects, mathematical objects, you can perhaps form sets like the set of all natural numbers or the set of real numbers. So let's go back a little bit. It seems important in mathematics to distinguish objects and other things that come around. Think of sets and classes in set theory, this difficulty. So objects should be the things with which you can do all mathematical constructions, so to speak, yeah, which allow you to form collections, sets, and types. And so in the Naproche system, this would somehow go like this, that you say an object is a notion. It's one of the types that I'm interested in, the type of all objects, and notion is the Naproche keyword for that. That is taken over from the FOL language, which is was the input language to the SAD system, which preceded our system. So in Naproche, you get these nice printouts in the second line from a LaTeX source, which looks like that. So there's nothing hidden there, nothing secret also around it, just what you know in mathematical writing. And then you can also look up in the system first-order translations of such a command, signature command, a command which wants to extend your language. And here you see the first-order translation, and it just says, well, it really just says we have introduced this unary relation symbol. So types as relations is the idea behind this. Unary relation symbol, and this is just a triviality, but this is just the internal way of capturing things to be consistent with other situations. So then you can go towards natural numbers, as we saw, and you want them to be objects because you don't want to do all sorts of mathematical things with them. As a LaTeX source, here you see the first order translation of that command, and it would say, it would translate this natural language statement into, well, every natural number is an object. Yeah? That seems to be the only thing that you can take out of this signature command. But then the word to you looks like that. Yeah? You have a domain of objects, and inside is a subdomain, a subrelation or so, a subtype of natural numbers. And then you inhabit that with constants. So in first order logic, of course, we have to worry about relations, functions, and constants. So here some constants are added. And if we jump ahead a little, how is it about set theory? Well, you would also say that a set is an object, because with sets you want to do all sorts of mathematical things. There are classes, like this Russell class or universal classes, which better be not an object to avoid contradictions. So the picture would be that classes lie sort of a little bit outside, but there's an intersection in the with respect to sets here. And in the previous slide, the natural numbers were just a subrelation there. But if you want to do more, you can axiomatically declare, and here this would also be a FOL statement in the second line, and it's a collection of all natural numbers. You would say, I make it a collection, and then it is a class. Yeah? It's sort of, the dot there goes into the classes. If you go further and say, I want to rather have it being an object as well, then that should be, of course, a set, and the dot would sort of wander from up there into this region of sets. Now, for the sets, you would require axiomatically as many set theoretic axioms as you like. In weak situations, maybe it's not necessary to specify much about these sets, but it's often good for larger formalizations to have basically all of Zermelo-Fraenkel set theory or something similar there. And the interesting thing is that pushing these natural numbers into the sets already is a strong axiom, is the axiom of infinity that one knows from set theory. Okay, and then more things have to be added. I think the errors are a little bit sort of have shifted, but for example, on these natural numbers, you want functions like the plus function and other things and so on, so you can think of populating this more and more. How do I deal with general structures here? Well, I would say a group is a set. I mean, this is perhaps a little bit questionable, because it seems to equate groups and sets, which it doesn't, because we know this is interpreted as this implication. So you would have within the relation set, you would have a sub-relation in the middle of the picture of groups. Yeah? So some sets are groups, and if I declare them to be a group, then they would have these things like the zero of the group, the addition of the group, the minus of the group, and so on. And I could declare axiomatically certain axioms about them. So how does that go on, this working with structures? Well, we can say a ring is a group, or I said additive group, perhaps on the previous slide somewhere. And then this ring brings along its own things, like its own one, its own operation here, and axioms with that. Yeah? So we take this very naive approach that is similar to what you would find in textbooks, that you would just say a topological space is a set such that. Yeah? And this set is sort of considered to be the domain, and this set is also the carrier of the notation, yeah, that you sort of refer to. When you say something is open in the topology T, and T was a set, then this set is also equipped with sort of some naming, which names the open sets or whatever in that structure. I mean, there are some difficulties with this very simple approach to structures, and really it could be done much better, and even you could do a very general structure approach like Adrian in his new version of Naproche is using, where these structures would be sort of, let's say, consist of all sorts of operations and so on. But this, I think, works quite nicely and models a little bit the naive approach often used in mathematics. So here's something for topology. A topological space is a set, why not? And then you declare, I mean, how do we go on? I mean, there are always these choices in formalization. Yeah? You could say a topology needs now the set of open sets or so, but in this sort of first order and relational spirit, I rather say that that I do it via a relation. Yeah? I define the relation of X being open in T, and I just say that that is an atomic, a basic statement or so. And this means I introduce a relation. It's sort of a dependent unary relation. Yeah? So the T, the topological space I'm considering, serves as a parameter, and then depending on the parameter, this or that may be open. Yeah? So instead of our dependent types, so to speak, are just dependent relations here. One could look, there's not much time, in the first order translation, and you would see this binary relation with the first predicate, with the first argument for X, and then there may be more arguments for the parameters. You could see that in the first order translation. And then you can put these things together. So what is a topological group? I mean, you can go two ways. You can say a topological group is a topology which has a group on it also, or you can go and say a topological group, and perhaps that's a natural way, is a group such that this thing is also a topological space, and then there is some connection between the algebra and the topology. And these are, I think, sufficient axioms for that. So the snippets of Naproche that you saw are from a formalization of perfectoid rings in Naproche. Warning, perfectoid rings are just a component of perfectoid spaces, far from the complete notion. So I just thought this is something I should try, and it sort of led Naproche to its limits, sort of. So I would warn people who would go on and say, no, let's formalize perfectoid spaces. But I think in principle, it should be possible. Because what I did is I followed the lean formalization and just try to basically go along the same path and do that in Naproche. So here is the file. When you write Naproche, you are automatically in LaTeX, and you automatically can use this literate style that you can write things around the formal content. Therefore, it looks a bit like a mathematical article. And if you sort of jump into this, then we can see certain things that we saw before. Yeah? For example, starting with the numbers, we said a natural number is a mathematical object. And of course, here it's a bit more again, and is a set. And so that is what we saw. So we saw these first three lines of the number formalization. And then, of course, it goes on to more and more axioms. The formal part of these texts are with a gray background. And the other things, the white parts, they are just comment, and you could have written everything, or whatever you're doing later, like pictures or table of contents and so on. Right, so this goes on, and you would see certain things that we have just indicated, like a group is a set, for example, and then we have gone to more powerful structure, like a ring is an additive group we saw, and this thing develops, and I can't go into all details. What I would like to say is that sometimes I do some simplifications, like for example, the final concept has to do with localization of rings and maybe quotients and such things, but I try to keep it low, and certain properties that are required, and I don't want to develop a general theory here, can also be done by congruences, yeah, so that I don't have to go to real quotients. So there's something about that, and so it's just, here's topological spaces, topology gets into it, a topological space is a set, etc. Then all these things are, of course, combined together somehow, and they really come together in this, these more technical chapters here on boundedness. Yeah, so it's important that certain things in rings are bounded with relation to the topology that we have, and so you have to see that the empty set is bounded, singletons, finite sets are bounded. So finite sets boundedness, this is of course done by some induction and so on, so that's the way. And if you go further, then you would end up, well, we're getting nearer to it. There are specific rings, certain properties, where all these components or all these theories come together. So here is notion of a specific element in a topological ring, and if such a specific element is there, then you can say a Tate ring is a Huber ring that has a pseudo-uniformizer. The Frobenius chapter, this is this mapping x goes to x to the p, where p is a prime number, arbitrary prime number. That is technically very important, so there is still some technical stuff to be done. We have to see that the Frobenius is indeed, well, what do you have to show in such a, it's just a definition in the end, where you have to justify certain things, yeah? And it's sort of a question, of course, how far you go with your justification. So the justification here is mainly steered by that all the things that I'm writing have the right form. Yeah? If I write something like x over y and use that in my mathematics and use it in a definition, then it better be that the y is not 0, so that I can do this definition. Or with other constructions, if you do something like quotients, you better ensure that you have an equivalence relation or congruence relation. So, and such things are proved here so that things are reasonable. Yeah? I mean, otherwise you could just define anything and say, oh, here's my definition, and believe it or not. So some justification is required, and so what do we do here? For example, that the Frobenius should take 0 to 0, 1 to 1, rings with ones here, and so on, and probably, yeah, and you see here I go to congruences, so I do something modulo so and so. I do that here for the addition, that it's addition preserving, multiplication, it should also preserve, etc. Technicalities. And then in the end, I arrive at perfectuate rings, just the definition of it. No examples, no further properties, but this is the end of the story. I just say a ring is perfectuate if, and now all sorts of things come together. I should say a lot of this, I already indicated that I do these things with quotients. Don't ask me for the algebra, I'm emeritus. This is sort of a notation, an abbreviation for something expressed via congruences. I would say that whenever I have an element of this right-hand ring, then I find something on the left-hand side, and then if I continuously map it over, the original thing is equivalent, here, to the thing that I started with, or so. Yeah? So there is a longish definition of that, but we don't have these things as objects because I wanted to sort of cut some corners. Right, and then if you look at the comparison, how it looks in Peter Scholz's article, there is, I think, quite some similarity. Of course, if I am free to choose my notation, I can make it rather similar to what you find in the original. Okay, so let's go back to the slides. So this is part of what I showed you. This is the final page that we also just saw. And how can we wrap this up? And I think we should, for reasons of time. Well, we are talking about theories which involve quite a lot of soft typing, for every natural number, this and that, every group, etc. And then subtyping, which is usual. So soft types, I would say, come from natural language. This is just the language that we use mostly. And then I would claim that this can be modeled quite well in first order logic and through type guards, of course. So soft typing gives you natural things about these types. It's not a strong type system, or not a good type system, because it's sort of allows so much variation that you cannot hope for the decidability of types or so. So type properties, if they have to be checked for the correctness of certain definitions, these type properties have to be checked by first order proving, because it's all in first order. But I would say that the ATPs we are using, E-prover mostly, sometimes vampire, is able to handle the first order tasks coming out of the soft typing. And in conclusion, I would say that first order ITPs, so Naproche is one of them, MESA is perhaps the first in that direction, can deal with rich mathematical contexts, and as we saw with the various structures that had to be put together to get our perfectuated rings. Thank you very much.